part 2 of Keith's presentation. Here we go.
All right, I'm going to talk about various protocols and file formats, and a lot of the stuff that we just covered will come back up again, and I may gloss over a few things as a result of that. This will likely run beyond the end of the hour because I really only need about half an hour to do my next topic, so I'm going to run this one a little bit long. So if you're interested in the underlying protocols, the underlying file formats, etc., you need to get good at Google and finding the various specifications. Many of the things that we use have formal specifications. Occasionally, those specifications are hidden behind paywalls and the like, but generally speaking, there is a version or some flavor of the specification available, and you just need to be able to find it. Some of the protocols that we use in the hobby are proprietary and have been reverse engineered, sometimes in a fairly complete way, sometimes in an incomplete way. But if you're really interested in understanding how some of those protocols work, you really just need to know, well, which of the projects implement those protocols, and look at the source code that those projects are make public, and you can generally get an understanding of how those protocols work. And of course, if none of that works, then you can go in and actually do the reverse engineering of the protocol. That can be a tricky and time-consuming process, but I've made videos in the past on reverse engineering things. All doable. So let's talk about some of the key protocol groups. I will touch on pixel data to the controller. We'll touch on pixel data to the pixel. We'll cover serial protocols, discovery protocols, synchronization protocols, and event protocols. I'll point you at specifications. I'll show you a bunch of tools that can help you understand what's going on. So let's start with SACN or E131. So there is a formal specification here. A second, because I did download it. I did. No, I did. All right. It is available here at this link. It's just a PDF. There are several versions of it. It has 127 bytes of header information and up to 512 bytes of data information. Unfortunately, there is very few useful bytes in that header. There's some tokens at the beginning that let you know that it is an E131 packet. There's a universe number, which is obviously important for understanding which universe that data is for. There is some synchronization if you happen to be using synchronization. There are some size fields. There's actually several size fields that need to be populated correctly. And there is a sequence number to tell you the sequence number of that E131 packet. The rest of the header is largely junk. And that's unfortunate because it obviously creates a whole bunch of overhead and makes the protocol relatively inefficient. It's one of the reasons why so many people these days have moved away from E131 in the hobby and moved to protocols like DDP, which are way, way, way more efficient in terms of their network utilization. You can have up to 65,000 universes if multicasting. If you're not multicasting, if you're unicasting, then essentially you're sending the data specifically to the controller, and there's nothing to stop you duplicating the universe numbers. As long as only one controller sees the universe, it doesn't care. This is the specification from ESTAR. They are actually the certifying body. They do this and ArtNet as well. And within this document, there's an enormous amount of detail about the various bytes and fields and how all of those values need to get set. These documents, while they have everything you might need in it, they're often not super clear to read. It really does take a certain amount of patience, and often it's helpful to have a worked example, some system that you can look at and see what's going on in the data. Things like Wireshark get really useful here, because you can start to pull E131 data off the network and take a look at the actual packets themselves. And in the case of something like Wireshark, it can also do things like show you or interpret at least the header fields, etc., of the packets, so that you can understand what's actually going on in those packets. But you will need to get fairly familiar with these things if you want to understand it. Now, you only really need to understand this if you are going to either build a controller or build some sort of thing that's going to be sending data to a controller, is when you might need to understand that. So a maximum of 65,000 universes. One of the things I often look at is the efficiency. So given that there's 127 bytes of header for every 512 data, that means that there's about 20% of overhead in every single packet. But it's actually a little bit worse than that, because most data in networks is sent in a frame, and those frames support 1,500 bytes. And so there's actually about 35% of the data or the network packet that's actually being used, and the rest of the frame is basically wasted by this protocol. So it's not very efficient, but it's very, very widely supported, and therefore it's often the default protocol on a lot of controllers. ArtNet's actually an older protocol. Again, it has a specification that you can access. The specifications actually are much more complex. While SACN and ArtNet both allow you to send 512 bytes of channel data, the ArtNet specification is actually a much broader specification. It supports a number of different packet formats. It supports a time code, it has eventing, it has discovery, and all sorts of things that you can do using it. So the protocol's a much broader protocol. But from when it comes down to sending data, the thing that sets it apart is it has a much, much smaller header, only 18 bytes and 512 bytes of data. So it means you've got fewer useful fields. It is limited to a maximum of 32,000 universes. That's assuming you're using a relatively modern version of E117. The older versions of E117 were even further constrained than that. So it has a relatively low overhead when you just look at the specific packet, but you're still not using much of the network frame. So it's still not particularly efficient. It's much less commonly used within the hobby, although professionally, ArtNet is used a lot more often, even than SACN, I think, in general. And that's just because of some of those other features that sit within it. The one that most people end up using these days is DDP. Now, DDP is actually a proprietary protocol. It does have a public specification, which you can access at this link here. The specification is a fairly poor specification when you compare the specifications back to E131 and E117, which are, full on standard specifications with everything laid out. The specification of this particular protocol is much, much more high level. Some things are covered in reasonable detail, some things are barely mentioned at all, and you've got to kind of guess what they're doing. They're not necessarily extensively used, and it just lacks that formalness and comprehensiveness of the other specifications. But on the upside, it's an incredibly efficient protocol with a 10-byte header and 1,440 bytes of data. You're getting something like 99.3% of the network frame is being productively utilized when you're using DDP. And that's why DDP is popular. DDP has been in xLights for quite some time now. Originally, I implemented it years ago because I was implementing some super low-end Arduino-based controllers that I wanted to receive network data, and I want the lowest possible overhead protocol, and I stumbled across DDP. Now, if you go to the DDP specification, you won't see MinLeon mentioned, but the guy that maintains the protocol is actually the developer of the controller firmware for the MinLeon controllers, and that's why you'll find that the MinLeon controllers all implement DDP natively, and actually will emit it to some of their downstream devices. So that's why DDP is so popular. The specification, like I said, is much less formal. It has got better over time. The first time I accessed this, it had very little information. It has got better. It does have some discovery elements to it, which it never had when we first implemented it. But yeah, it's quite limited, and it assumes a whole bunch of things, right? That, you know, when it talks about RGBW and RGB, etc., it's often not necessarily referring generically to those things, but to some of the specific pixel types that that MinLeon support and things like that. Yeah. What storage means, etc., is not clearly laid out anywhere. It just says storage. If set, the data comes from storage, if not, a data field. But that it doesn't really explain what that means or how you use it. So it's quite a difficult protocol. And so fortunately, there are a number of implementations of it that you can go out and source to see how it's handled in things like xLights or FPP or the pixel sticks. So I would definitely do that. If you go to GitHub, xLights, and go to the code, the key folder you need to go into is, if you go into the xLights subfolder and then the outputs folder, this is where you will find all of the protocol implementation. So if you want to see how xLights does E131, there's the E131 file. If you want to see how xLights does DDP, there's the DDP source file. So you can jump into there and take a look at how a sender of that protocol interprets it. If you want to see a receiver, then you'll need an open source implementation. The Pixel Stick project is often pretty good for this. But at least for some of the more common protocols, Martin's done a really good job of implementing those. And the code base is a lot smaller than something like FPP. And not so much on the input protocol side. Also, everything, the input protocol side of FPP is reasonably available and accessible. But the Pixel Stick code base is just a lot smaller. So if you want to look at how to implement code to receive DDP or receive E131, then the Pixel Stick the Pixel Stick code base can be quite useful to take a look at. So what about pixel protocols? There are many chips out there. You know, we talk a lot about WS2811, and you know, people are aware that WS2812 and 2811 are essentially the same. But you know, there are actually hundreds of chips that do various amounts of pixels. And located within the GitHub within xLights is this particular file here, which we'll open up. And this file here contains a table. This is a table that I pulled together largely on the back end of the work that I was doing around the Falcon controllers, because we implemented so many of these pixel protocols, where we went in and took a look at each of the various types of pixels, etc., and often captured all of the alternatives. So 2811, the protocol that most of you probably use, there's actually a whole bunch of different chips that all implement essentially the same protocol. And so this table is something that, that I maintain just to keep track of all the new chip types that come out and which protocols that they support, etc. They're all they're all very, very similar at the end of the day in terms of what they do, but there's variations, right? In terms of, are they 4 channels or 3 channels? How many bits of data is there? Most of them are 8-bit, but these pixels here, these GW6205, they have 12 bits of data, right? So a much broader color range. Some of the pixels require 4-wire rather than 3-wire. That means that they typically have a clock wire rather than just, I'm not talking about those WS2811s with the redundant data wire. Some of these pixels actually have a 4th wire for a clock signal, which controls when the data is read. There's definitely 16-bit pixels out there, which obviously provide a much finer grain control of the color of the pixels. So this table, if you're ever interested in understanding, whether a particular chipset is compatible with 2811, and therefore with your controller, this can be a useful place to go looking for that information.
Does xLights catch? Does xLights? Sorry, Keith. Does xLights catch you if you put in the wrong protocol for a controller, or vice versa? If a controller can't support it, does it flag somewhere or no? I think it does for some cases, right?
It does if you've defined what controller it is. So when you set your controller type here, and you come into your prop, and you come down to your controller settings here, right? It knows these are the protocols that controller supports, and it will only offer you up the controller protocols that controller supports. Now, if you, and this thing here is not on a controller, right? So when you click on this, you get a much, much, much longer list of protocols, right? Because you get access to every protocol that's out there, because this is not on a controller, so it doesn't know how to filter the list down.
Okay, thanks.
Yep. If you're using some of the more, so once you get outside of the WS2811s and the 4-channel equivalents of that, finding controllers that support those pixels gets harder. Some of the older pixels like TLS 3001 or the GECEs, there's a few controllers that might support those. But the other more esoteric ones are fairly difficult to find controllers for. Probably the most extensive support sits with those Advotech and Falcon controllers that have implemented a whole bunch of them. The Mignon controllers also support several protocols, although it's a very specific set, and a lot of them you actually can't tell what protocol they are because they're hidden behind a branding that they use for the particular pixel types. The pixels themselves also have a protocol, how the signal is received, and here you're going to need to get good at finding data sheets. So this here happens to be a link to a WS2811 data sheet. These data sheets are electrical data sheets, they're chip data sheets, so they tend to be quite detailed, they're quite physical. They have a lot of data in them about timing and voltages and the like. They may have pictures like this. This one's pretty good. This one's on the Adafruit site, so you can imagine those guys do a very good job of making information available and putting some of the best quality information up. But to be honest, that's not how they all are. Here's a slightly different one. This is the MY9291, right? It's a single pager. There's no schematics. There's no detail of timing, right? You basically have to guess exactly what the protocol is and how it works. Even that's not that bad compared to something like this one. The only data sheet available for this SM16726 is in Chinese. On the upside, this Chinese is selectable, so you can use Google Translate to try and get some understanding. And this one has, I think, some timing pictures. So you can work it out, but it's very difficult. It can get very time consuming when you're implementing the protocols that are like this. This is the WS2811 is what's known as a one-wire protocol. Like I said, the versions which have the redundant data wire don't really change that. The data signal is only on one wire. And the reason that's significant is because they're quite speed sensitive. While they don't care so much about variations in timings between the bits that are sent, the timing within the bit becomes quite important, because what happens is these WS2811 pixels, they detect the rising edge at the beginning of the bit, and then they wait a period of time. And if that period of time gets you into this low section, then it's going to read the data as a 0. But if it's in the high section still, it's going to read the data as a 1. And so your controller, which is outputting this data, needs to get this timing here quite accurate. Now, when I said that there were multiple chips out there that implement the WS2811 protocol, and this timing up here, the reality is they don't implement all exactly the same timing, and they've got different tolerances, etc. So it is possible that even though these chips, we say that, look, they're basically the same, if they happen to have a timing that's right on the edge of the particular timing that a controller supports, then you may have problems driving them. There were some pixels that I think it was Holiday Coro was setting that some controllers were having problems with, because the timing of them was right on the threshold. And if you had particular firmware, some controllers struggled to drive those pixels. They wouldn't read correctly. Some controllers will allow you to fine tune the timing here. They allow you to sort of stretch and shrink the timing, but that's not super common. These things typically have what's called a reset time. So when you're clocking out all of this data bit after bit, byte after byte, if the line ever goes low for more than 50 microseconds in this case, what happens is that the next time the data appears on the wire, the first pixel assumes that data is for it, right? So you can clock the data out with varying speed, but at the end of the day, you can't have long pauses, because it will then start to read the data again from the first pixels, right? But yeah, timing can be quite important. Normally these things run at 800 kilohertz, right? So each one of these cycles occurs 800,000 times per second. So it's quite fast. And that timing drives the maximum number of pixels that you can support on a string for a given frame rate. Because obviously, if it's doing 800,000 bits per second, then you can, and you've got 24 bits per pixel, and you have to finish everything in 50 milliseconds less the 50 microseconds that you're going to have as a pause. That timing allows you to work out the maximum number of pixels that you can drive on a string at that frame rate. It's also why when you change the frame rate, when you make the frame rate higher, you get less time, so therefore you can drive less pixels, and that's why controllers reduce the pixel count at higher frame rates. It's got nothing to do with the overhead. Well, it's not necessarily got anything to do with the overhead of handling the data as it's coming in. It's got to do with this timing, or the amount of time that it has to clock the data out to the pixels. The challenge with this as a format is, and you see this because people have all sorts of problems with pixels flickering and not responding correctly. And again, I made a video on that a couple of years ago at VCS, which you can find on the VCS YouTube site, where we talked about, sorry, I'm trying to find it. I've got it here somewhere. Too many windows open. This presentation here, ever wondered why your pixels flicker and how to fix it? And so we went in and talked a lot about what happens to the data on the wire. But one of the things that happens to this data on the wire is that while it might start off as a nice square wave when it leaves your controller, by the time it gets to the pixel, it is rarely a nice square wave. You get rounding of the corners, you might get shortening of this high period, And you can see that because it's quite sensitive to the timing here, if this high period shortens down too much, it will start to get read as a 0. Also, the height of this is important, because only once it gets to a certain height will the pixel actually read the data as having been high. And so with the rounding off that occurs of the corners of this square waveform, it essentially reads it as a much shorter waveform than it really is. And so you get all sorts of anomalies with pixels getting read. So that's why you've got to be careful around distance with driving these pixels. One of the things that made these pixels extremely popular is this actual waveform and format and speed, etc., is actually very similar to SPI, which is a really common microcontroller signaling protocol. So when the people were first driving these things, they would just put it on a port on the microcontroller that would support SPI and send the data out. It's one of the reasons why the PiCap originally supported a couple of strings of pixels, was because there were 2 SPI ports on the Raspberry Pi, and so it could drive the pixels using SPI. These days, of course, even the Raspberry Pis use a number of different mechanisms for outputting this signal, but this is a signal that they need to output. Now, there are other protocols. A very old protocol is called WS2801. Again, datasheet available on Adafruit. This one is different because it's actually a 2-wire protocol, meaning that there's actually a clock signal alongside the data signal. And this is useful because the clock signal allows you to basically tell the pixel when to read the data value. And this has 2 impacts. One is, obviously, you can time the clock such that the signal is likely to be in its best possible state. It also allows you to run the pixels at varying speeds, because while there is a reset time that you need to be conscious of, the reset time is much longer. It's 500 microseconds in this case. And the timing of the pixels themselves doesn't need to be as rigid. You can have lots of timing variability. As long as the clock arrives at exactly the right time to sample the data, it will read just fine. This allows you to run these things up a lot faster, and not the WS2801s, which are a very old pixel, but some of the newer clock pixels. Whereas a WS2811 will run at 800 kilohertz, you can run some pixels as much as 30,000 kilohertz. Because they're using a clock, and you've got greater control over that signal timing. But because the clock's there, you can also run those pixels a lot slower, and they'll still work just fine, because the timing is not inbuilt into the pixel. The clock controls the timing of the pixels. As I said, though, pixel protocols can get a lot more complex than that. You know, they don't have to be just 3 channels. They can be 4 channels. You can have 5, 12, or even 16 bits per channel. So lots more color depth. A number of the protocols have things like lead-in bits at the beginning of each frame, termination bits at the end of the frame, even lead-in bits at individual channels. So, you know, implementing all of these protocols is a significant overhead, which is why lighting controllers, which are really specifically designed for the hobby, tend to just do WS2811s and maybe the 4-channel equivalents, because there's a lot of overhead and work in supporting all of these various other configurations. There are pixels out there that allow you to send a special data stream out to the pixel, which will basically instruct the pixel on how to apply things like brightness and gamma. So those things can actually be applied at the pixel level. Yet they're often optional, and even where a controller supports a pixel like that, they probably don't implement that component of it. It's not mandatory. And then you get pixels which use totally radical protocols like Manchester encoding of the data. So the WS2811 protocol is really simple. You can look at it and immediately see, you know, the longs and the shorts and the ones and the zeros. It's really easy to see on the wire. Manchester encoding is entirely different. It's the transition from low to high that indicates whether it's a 1 or a 0. And so it's much harder to read on the wire, and it's much harder for a controller to produce generally. If you want to see the implementations of various protocols, a great place to start is the Fast LED library. The Fast LED library is an open source library that's out there. It supports a number of different pixel types. In fact, it's got quite an extensive pixel type support. You could build a very low-end controller using Fast LED. It doesn't scale very well. Outside of maybe the Pixel Stick, which I think used Fast LED at one point in time. I don't swear to that. Because it's really optimized for projects that have a single string of pixels that they want to control, and that's why Fast LED was written. Most controllers would use a more advanced library, but it does let you play with something that will output a protocol for a particular pixel type and see a reference implementation of it. Obviously, the Pixel Stick code is also there, and the WLED code is also open source. And so you can take a look at the WLED implementation of some of the Pixel protocols. Again, they tend to do a more limited range of protocols than the Fast LED library, which is much more extensive. DMX. There is a formal specification of DMX. It is a serial protocol. It only has 512 bytes of data plus a 1-byte header. OpenDMX and DMX are very similar electrically, but the packet header is different. Unlike and we tend to put these serial protocols into a slightly different class. We put them closer to the controller protocols rather than the pixel protocols. But in reality, DMX is more of a pixel type protocol. In fact, there is a pixel protocol that is purely based on DMX. But some controllers will accept data over DMX. So some of the Advantech controllers and the lighter arm controllers will accept data over DMX. Generally speaking, all controllers, all the things which are attached to the wire see the same data. So each of the devices need to know which data they're going to pull off. So they'll see all 512 channels of data, and they'll know that when it gets to byte 36, that's the data I need to pull off, and it might pull off the next 10 bytes or something. That also means that it's possible to set multiple devices to the same channels and have them operate exactly the same way, because they're all seeing the same data. DMX is always 250 kilobits per second, which obviously limits, but given that it's only sending 512 bytes of data, that's not such a big deal. And you do need to electrically terminate the signal in order to manage signal reflection. If you don't do that, then devices towards the end can have problems. And again, the VCS presentation on pixels flickering, I show what that does and why it works. But yeah, it's just a serial protocol. It looks like any other serial protocol. It has start bits and stop bits. It does require a low period at the beginning before it starts to send the data. So it's not just a straight serial port that you just transmit data on. There's a little bit of setup and control that you need to do to make sure that that works. Renard is another serial protocol. The Do-It-Yourself Christmas has a bunch of documentation over the Renard protocol. The Renard protocol, apart from the Renard devices, not commonly implemented. Those things are still available though, and people still do use them in the DIY space. They're essentially the poor man's Lightorama controller. They were always significantly cheaper. They were nowhere near as professionally built or anything, but when people were trying to get in the hobby and Lightorama controllers were hundreds of dollars, you could often get the Renard controllers a lot cheaper than that, and a lot of them are build them yourself. So for people that really enjoy the total DIY side of the hobby, they were quite popular. It's also a serial protocol. It's also RS-485. It's also 512 bytes of data. It does allow support for multiple speeds, and that can be good in situations where you've got, electrical interference and the like. Again, you should electrically terminate it. It does have a lot of framing overhead because it only allows the value 7E to be legal as the first byte in the packet. And so if you want to set a particular channel to 7E, then there's some additional additional mucking around that needs to happen in the controller to send a 7E as a data value to a particular controller. So that makes it a little bit more difficult to use. Lightorama. So Lightorama's protocol is entirely proprietary. There is no public specification for it available. And unlike DMX and Renard, it doesn't just send the channel data. It's not just a question of how is the data encoded in the signal. If it was purely that, then a full reverse engineering of the protocol would have been done years ago. And even the implementation of Lightorama in xLights is an incomplete implementation of the Lightorama protocol. It implements mainly the stuff that supports the older controllers, the old AC type controllers. There is the Law Advanced, where Gil reverse engineered some of the more high-end components of the Lightorama protocol, driving some of their Pixie controllers and things like that. But even that was incomplete. I don't believe he implemented the full protocol, and that explains why those things tend to max out at a certain level of a certain number of channels. It does support macro type commands where the controller can act upon an instruction. So rather than setting the brightness of every channel and the controller just dutifully following it, you can do things like send it a command to tell it to shimmer a channel, and it will shimmer the channel internally within the controller. You don't have to turn it on and off, which allowed the shimmer in the Lightorama controllers to look better because it was the controller doing the shimmering rather than xLights sending out a frame every 50 milliseconds or 25 milliseconds. You can also do things like dimming, which means that you can often get a much finer a dimming control, because again, you're not sending the brightness once every 20 milliseconds or 25 or 50 milliseconds. You're sending an instruction and saying to the controller, please dim this thing over the next few seconds, etc. And then it takes care of working out, well, exactly what PWM signal would produce that dimming. It also can do things like compress instructions for multiple channels into a much smaller amount of data. And so, setting out data to set all the pixels on a Pixie controller red doesn't require you to send thousands of red channels. It can often be abbreviated into a much smaller instruction. The challenge is when you do need to send individual channel data, it has a large amount of overhead. So the original implementation of Lightorama for in xLights, which basically used this mechanism, had about 6 bytes of data being sent for every byte that the controller would receive and respond to, which meant that xLights used to top out at about 96 channels, which was 6 times 96 bytes of data that had to be sent to control those channels. The advanced law stuff that Gil implemented does a bit better than that. The Lightorama also have adapters that support very high speeds, and so they have, I think it's the red adapter. The black adapter is the slow speed. They have a red adapter which allows you to crank the speed up to, I think it might be as high as 1.5 megabits per second. And that's obviously necessary if you're going to send serial data. If you're going to send pixel data over a serial port, you're going to need a very high data rate in order to get the data there. So that's the Lightorama protocol. There is no reference. You can obviously look at the implementation in xLights, but yeah, that's all there is. All right, discovery protocols. There are a number of discovery protocols. Discovery protocols are the protocols that are sent out when you do things like press the discovery button in xLights, or go into FPP Connect, or run the xScanner tool, it will go out on the network and find things that are lighting related. And it does that using a variety of discovery protocols. When you click the discovery button on the front page of xLights, it actually uses all of these protocols. It does the broadest possible scan to see if it can find things. In the case of FPP, if you're going to be, if you want to really get behind the scenes, there is some documentation around the packet formats in the FPP GitHub. It's this control protocol file, which talks about the things. It's not a very expensive set of documentation. I mean, all the fields are shown, and there's a one-line description of what goes into each one. You won't find a prose-like discussion that talks about how to use it. So you'll probably also want to go and take a look at some of the implementations of that protocol. Implementations, like I said, xScan is a great place to look because it's got a little bit less clutter around it, although it does use a lot of the common code from xLights for it. xSchedule also has controller discovery in there as well. FPP, if you're looking at this FPP document, you'll see it's actually called here the ping packet. This is actually the discovery. Discover is actually one of the values that goes into the subtype here. And when you send this out, all of the controllers on the network that will respond to this will send you back data. It's not just supported by FPP these days. There's a number of other controller types that will respond to an FPP packet. Typically, it's those controllers that do allow you to use FPP Connect to upload sequences to them. So things like the Falcon, I think the Genius controllers will respond to it, as will the Pixel sticks. Not sure about WLED. It's typically broadcast or multicast out, and then you listen to the responses to see what you can find. ArtNet also has a discovery protocol. The ArtNet discovery protocol is really more designed for fixtures to respond to. It's really for finding, devices within your theatre layout or something like that, given that where ArtNets come from. The ArtNet specification, which was on the earlier slide, does contain a description of that discovery protocol. It's nowhere near as extensive, but it does exist. DDP, oh, sorry, it was ArtNet. DDP also has discovery. But there is a discovery. There is the ability to use discovery in DDP to go out and find things. And again, if you want to take a look in xLights, you can see an implementation of the DDP discovery protocol. FPP sync. So these are the sync packets. Again, the control protocol for FPP does describe the sync packet format. It's this one here. There is also a project. This is my bit bucket. This is for my non-xLights related code. And if you go to this location here, you can download it. There's a compiled version in here, so you don't have to build it. You can go into the bin folder. There's actually a program here that you can run on a computer on your network. It's Windows only. This is written in .NET because when I'm lazy, I write in .NET. You can run this on your network, and if it's connected to the network where your show players are, etc., it will monitor for the sync packets and will show you in a user interface the sync packets that are being received. So if you ever want to visualize the sync packets or check that sync packets are actually being sent, that utility can be useful to see what's going on. The thing about the sync packets is FPP doesn't send the sync packets in a consistent manner. It doesn't, for instance, send it every second. Instead, what FPP sync does is it obviously sends a sync packet when a sequence starts. And then for the first few seconds of the sequence, it sends the sync packet with a relatively high frequency, just to make sure that all of the remotes are seeing it and getting it. And then it backs off and sends it a slower frequency through the rest of the sequence. And then at the end, of course, it will send a stop sync packet to tell any of the remotes that it's stopped playing. That's not a bug, that's intended behavior, and it's there to ensure that there's good resilience around the sync protocol. Obviously, sync is really popular when you're trying to run controllers over Wi-Fi. All the protocols that we've talked about across the network break down pretty quickly over a Wi-Fi network. Wi-Fi networks just do not deliver the consistent performance and can be affected by devices that are in poor Wi-Fi reception level areas. And when you're sending data out, it can lead to one slow controller impacting the network in general. Whereas FPP sync is obviously a very small packet format. It's typically less than 30 or 40 bytes, depending on the length of the song name that you happen to be playing. So it's a very small packet, and it's sent very infrequently, rarely more than once a second. So it's very low impact on your network, which is why it's so popular in some situations. Time codes. So outside of sync packets, the other way in which shows are commonly coordinated is using time codes. Time codes are useful because devices outside of our controller type devices often support them. So one of the most popular ones is SMPTE. This is an interesting timecode protocol because it actually operates over an audio channel. It's actually encoded in one of the audio channels. So you might have, if you've got two channels, you might have one channel which contains the SMPTE audio track and the other channel which contains a mono representation of your music. Or if you've got more channels of audio, then obviously you can set a channel aside for it. Obviously, much harder to program to. There is a library out there called libltc, which is used by xSchedule when it does SMPTE support. And so this is a library that you can download and include in your project, and it will both create the audio and send the timing out over an audio output, but it will also accept input from an audio device and read back out what time your sequence should be at. ArtNet also has a time code. Again, refer back to the previous specification links for the ArtNet timecode link. And if you're using MIDI devices, there's also a MIDI timecode as well, which goes over a serial line and allows you to synchronize multiple devices together. Generally speaking, in the hobby, though, most people would use FPP sync. But if you're looking to integrate it with, firework control devices and things like that, obviously none of those things supports FPP sync, and you're going to need to start to look at these other timecode supports if you want to integrate with them. I believe, I won't swear to it, but I believe FPP these days does support at least a couple of these. I know xSchedule supports them if you're doing those sorts of integrations. Events, there are also packets here. There are also event packet formats which are defined in the FPP specification, and the newer equivalent, which are commands. These are ways to send an event or an instruction that something should happen between devices. I'm not even sure that the event packet works anymore. I think that's largely historical these days. I think FPP only supports the commands. You can launch them using the FPP API. The FPP API documentation, if you've got an FPP device, you can access that via the help menu, and it will give you instructions on how to trigger a command, or you can send it over the control packet. There are other eventing protocols. ArtNet includes events. Again, see the events specification. And obviously MQTT, which is commonly used in things like home automation and the like. There's also eventing support there. And again, FPP and xSchedule include some integrations with MQTT if you want to trigger certain actions more commonly, from outside of show technology. MQTT can be used. Let's talk about file formats. The FSCQ file format also has a specification. It's actually in the same folder as the control packet, but it's a separate document. Again, it's a fairly limited specification. It's, everything you need to know is technically here. It's just not necessarily easy to read and understand. There are two file formats. There's the 1.0 specification and the 2.0 specification, but then there's a whole bunch of subflavors under the 2.0 specification because it supports a variety of compression types, and it also supports sparse formats, etc. So the data in it can be quite different. And there's also been some recent changes with the ability to include things like commands inside FSCQ files. So the format has continued to develop over time. If you want to understand the format outside of that, again, in my Bitbucket, I do have a program here, which is again freely to download, runs on Windows. This program will basically allow you to drop an FSCQ file onto it, and it will basically dump out all of that header information that you can see in the specification here. So it understands version 1 and version 2 files. It will go through and it will tell you exactly which channels are there, how many blocks there are, the compression types. If it's a sparse file, it'll tell you exactly which channels are included in that file, etc. So if you've got an FSCQ file and you really want to understand what's in it, that utility can be useful for understanding what's inside that FSCQ file. I haven't updated it with these other variable length header stuff, and something I may get to at some point. But that should still work. It won't show you the data. The FSC, this tool that here is really about just dumping out the headers so you can see what's actually in it. The xLights files, so the xLights networks, RGB effects, and the XSQ files, they're all in XML format. They are all undocumented and not to be relied upon. We can and we do change the file formats from time to time. The file format changes are never documented. They're never even announced. Sometimes you might see in an announcement something along the lines of, look, if you implement this particular upgrade, then you won't be able to go back to a prior version. That suggests that there is something that's breaking in the change where we can upgrade it going forward, but we obviously can't downgrade it going backwards. That's relatively rare. I don't think we've had that happen for a couple of years now. I think the last significant breaking change was the move to the controller tab away from the network tab. When we had the networks tab, data was stored quite differently in that file. But if you build tools or build things that are dependent upon the file formats here, you just need to recognize that they can and they will change, and you will not get told about it. In fact, the contents of the files often change with various enhancements. When a new effect is added, obviously new sorts of things start to appear in the file. When an option is changed on an effect, it can change what gets stored in the file. The developer often doesn't even know that they've changed it at that point, because a lot of that stuff is actually quite abstracted away from the developer when you're maintaining xLights. So the only thing that we do is if we do change something which changes the way something is stored, we will write upgrade code to upgrade older files. So you're still largely able to load files from 5 to 10 years ago in xLights, and they will still largely load. But that's because we write upgrade code. We don't write download code. So use at your own risk. That said, it's an XML file. You can get in there and poke around and make your own conclusions about things. The final thing I thought I'd mention, because there is documentation on these things and it's worthwhile knowing that they're there and often people don't, is there are a number of APIs that are available. So the first one is in this file here is the xLights API. So in the last couple of years, we've created the ability to automate xLights. So for today's presentation, the presentation I'm about to do on xSchedule, I needed to make sure that my show had all of the sequences all rendered and ready to go. And so I ran a batch job, which did the batch render without even opening up. I didn't have to open up xLights. It opens up xLights, does the batch render, closes everything down, etc. And that's all done using the various APIs and the xLdo command for those that are running things from the command line. So definitely worthwhile understanding you can control xLights remotely, which is not as useful as controlling your show player. So again, xSchedule in this case has an API which is also documented, and you can poke through this and do extensive over the web control of xSchedule. There's literally almost 100 APIs that are available in xSchedule. Obviously, FPP has a similar and more similarly extensive API set. Again, you would access that from the help menu in FPP. It also has, because it's online documentation, it also has the ability for you to do some, to actually call the APIs from the web interface, which can be quite useful as well. The rest of the controllers out there, a number of the controllers actually do have APIs. They're not always publicly documented, but some vendors will make it available. I know Falcon will make the API available to you. I know Avtech has made theirs available to me in the past. Their upload packet format, they sent me a specification when I asked them for it. Like I said, FPP obviously has extensive documentation on its API. And obviously for the others, xLights, we've generally reverse engineered or implemented, like I said, based on information provided by that vendor. So if you go into xLights, not into the outputs folder, but into the controllers folder, you'll see there is a file here for each of the controllers. So you go to the Minleon folder. There's no API implemented for Minleon, but obviously we're able to control the controller, and that's done using a bunch of web requests, etc., which we've reverse engineered by looking at the web page. Whereas the Hinkspix has an API, the Falcon, the V4 has an API that can be called, FPP has an API, can be called, I think Experience probably do as well. So that's the APIs. Any questions? Everyone's been very quiet. No questions.
Two questions. One's probably obvious. You can't, going back to your protocols, you can't mix and match on a port, right? Or is there might be a couple instances where
so you mean pixel protocols?
Yeah.
Generally, no. There are, for instance, with WS2811, there's a 4-channel equivalent to WS2811. I think it's APA 104 or something, or maybe it's 109. I can't remember. I always mix those two up. They're slightly different. They're essentially the same protocol. One's just 4 pixels, 4 channels, one's 3 channels. You can technically mix those on a port if you really want to. But no, generally not. The port, and in fact, on many controllers, on the Falcon V3s, you could specify a different protocol for every single port. And the reason you could do that is because it was all implemented on an FPGA, which means you effectively had a separate routine running each port. Whereas on the Falcon V4, you can only set it per bank. So, the first 16 ports all have to be the same protocol. The second 16 ports can be a different protocol, but they have to be the same protocol. And then you get to the Advotech controllers, and on the Advotech controllers, you can support all these different protocols, but each controller can only support one protocol at a time. So every port on the entire controller has to be the same. Some of the protocols also don't work with smart receivers. The nature of those protocols just makes it impossible to do.
And a question from chat. I don't know if Dirk wants to take off his microphone, but he says, have you experimented with the XBEE protocol, which seems less impacted by interference than typical Wi-Fi, even though it runs in the same frequency spectrum?
Oh, so this is
XB, like the letter X.
Yeah, that's one of the home automation. That's one of the home automation protocols. It's no, I haven't, but those protocols aren't designed for high traffic, and often these things struggle with the varying signal strengths impacting on other devices. But Wi-Fi is just it's high volume, right? People are watching movies and everything else over it, and so those things work. Those things work really effectively due to buffering. But unfortunately, in the lighting hobby, it's not really practical to buffer, both because the devices that you're sending to rarely have the memory to buffer, and because at the end of the day, you need to respond instantaneously. No one complains when they jump ahead in their movie and it takes 30 seconds for it to catch up. People would complain if it takes 30 seconds to start a song. So, yeah.
If you purchase lights from Home Depot or Costco, is it a matter of like ripping one apart to see what protocol they are, and might they then work with xLights? Is it that simple?
Look, there are multiple. Until you've got a set of lights in your hand, and more importantly, you've got the controller, it's hard to know exactly what the protocol is. I made a couple of videos. I never finished them because I've been so busy this year. But I spent a bit of time reverse engineering the twinkly pixels. I can tell you there is not a controller on the market today that will drive twinkly pixels disconnected from a twinkly controller. At least not the residential ones. And they never will, because at the end of the day, those pixels are, they don't even have 3 wires. They have 2 wires, which means they provide both the power and the signal on the same wire. And there is no lighting controller on the market today that will do that.
All right, cool. Any other questions, guys? Is this a good break time again? Are you ready to move on to xSchedule? Or have you got more? All right, I'm going to stop recording. Any other questions?